information with the telescope that looked like the image height over the object height. So that's the way that we used to define it. And oftentimes we still do define it that way. But we can also define it as theta prime over theta naught, where we call this an angular magnification. The problem with using image height over object height for objects that are really far away is, for example, you're looking at the moon, that distance relative to the other distances in the problem is essentially infinity. And so it's not, you can still do it that way, but it's not very convenient to do it that way. And so what we do instead is we can take a picture like this, where we have the parallel rays coming in. We can draw this distance here. That's the focal length to essentially the eyepiece lens. And then from the center of the lens, we can say that that is the angular displacement of the object that you're looking at. So in other words, if you're looking at the moon, let's say the moon is up here, you're going to sweep out a certain angle and looking from one side of the moon to the other. Okay, and so we could call that theta naught. And so that's the original angular size. Where we define this angular size as the angle that we sweep out in looking from one end of an object to the other. And this is truly not the same thing as the true size. Because I can look at this pen up here like that, and it sweeps out an angle maybe of 90 degrees. But then I know it's the same size, but it looks smaller when it's farther away. And so I can measure that apparent size by the angle that I sweep out and going from one side of it to the other. So let's imagine then that the moon is sitting here, and you're kind of looking at the center of the moon maybe along the axis, and then you're sweeping up through that angle. So you're looking, this is showing more of an angle than it would actually be for the moon, because the moon is actually, only has an angular size of about 1/2 degree. And the same for the sun. They have the same angular size. Of course, we know the sun is 400 times bigger diameter than the moon, but the moon is also 400 times closer. And so those two effects just compensate, and that's why a total eclipse of the sun is possible, is that the moon is just at that optimum size so that it can cover up the sun and look from our point of view so it has the same angular size. So that's our theta naught. And so here we can say, in terms of this ray diagram, that the tangent of theta naught is equal to the opposite side, which is h prime, over the adjacent side, which is the focal length of the objective lens. Okay? Because that's where the light's coming in from. It's coming in as parallel beams from a distant object, and it's being brought to a point of focus there. But now, what we do with the secondary lens is we expand that angle. Okay? And so here, call this theta prime. We can get this angle theta prime by looking at the tangent of this angle, theta naught. Okay? And so if we look at this angle here, which is essentially the same as this angle there, that goes right through the center. measuring these things from the same point. So here we have to measure it from the center, like that. Then we get that the tangent of theta prime is equal to h prime over fe. Now remember, we're putting the image for the first lens just inside of the eyepiece focal length so that we can get almost infinite magnification. But not quite infinite, because if it were infinite, then you'd be spreading the light out over an infinite amount of space, and you wouldn't have any resolution, so you couldn't see it. And also, there's slight imperfections in the rays themselves. And so we want this image to be close to, but not quite at, the eyepiece lens so that we can have an extremely large but virtual image magnification. So remember, when it's exactly equal, if we're right on it, then these rays would come parallel and the image would be at infinity. So you don't want that. So you're getting close to that. And that's the whole key here, is you put the image for the first lens just inside of the focal length for the eyepiece lens. And so that's what I discussed in lab in a good amount of detail, but I just said it all again. And so now, what we need for angular magnification is, because we're looking at fairly small angles, we can say this is approximately equal to theta naught. Because the sine of theta and the tangent of theta and theta itself are all approximately equal as long as theta is less than about 10 degrees. You're not going to be looking through 10 degrees at an object in your telescope. You know, you're going to be looking at things half a degree. So that's the biggest thing you're going to look at is the moon, half a degree. So that's your small angle approximation as well in effective. And so we can say that this is theta prime, too. It's the tangent of theta prime. And so now if we want the angular magnification, that's just how much more angle we've stretched the image out through. Okay, and so that's going to be theta prime over theta naught. But that's the same thing as tangent of theta prime over the tangent of theta naught. So that's h prime over fe divided by h bar. Used to doing that from 2HC. Divided by f up. Then the h primes cancel. This is 1 over FO. So that gives us FO over FE. So that's approximate, but it's close enough. So that's our angular magnification then, is the ratio of the focal lengths. And remember that in lab, what we were doing is making the distance between the lenses to our first approximation equal to the sum of the focal lengths of the two lenses. And so that's how we get close. And then from there, you can do your final little adjustment to get your telescope to work. Are there any questions about that? Okay, next, I wanted to, now we've already talked a little bit about reflecting telescopes. They are much more effective for gathering together large amounts of light. We discussed why that's true, and so this is basically conceptual, and I feel like it's already been discussed well enough. You have this kind of focus where you bounce the light out through a lens, and so instead of having a lens here, you've got a parabolic mirror, but it does the same thing. It brings the light to an image point up here, but you don't want it inside the telescope because then you'd be blocking the light. And so you bounce it outside of the telescope to a point along the side. This is called a Newtonian focus because when Isaac Newton invented this kind of a telescope, he wanted to drill a hole through down here. He wanted to put a diverging mirror here and take the light that's coming together and bounce it down to a more convenient viewing reference point here. But it took him forever to make these mirrors, and he didn't have a high-speed drill in those days, and so he kept breaking his mirrors. And so after a while he goes, this is enough of that. And so he just took another mirror and he bounced it out along the side. And so that's called the Newtonian focus. But you also have the Cassegrain focus, and that's more like what we have here. In this kind of a situation, the light comes in like this, parallel beams, it's brought toward a point of focus, but then here you have a diverging mirror. And then that slows. It doesn't cause the light to spread out, but it causes it to converge less rapidly. And then that image is just inside of the focal length of the eyepiece lens. So here's the eyepiece lens here. And the image ends up just inside of the focal point for the eyepiece lens. And so the rest of it is pretty much the same. That's what I showed you before for the refracting telescope. It's just the way that you get that light to form the image that is different. And so in a really big telescope like this, you're better off with this kind of a mirror. But if you're looking in from the side, you're better off from this kind of a mirror. So if you've got a telescope that you can stand next to, it's not that big, you can stand next to, then you may not want to be crouching down way below it like this, because it's not up in the air. So it would make more sense to have it bounce out on the side. And so the kind of telescope that you would buy might more likely be a Newtonian focus. But in some big telescopes, they've got it set up so it can go either way. You can interchange the different kinds of mirrors. You can either have this kind of a mirror, or you can have the diverging mirror, which I don't have a picture here, that would be like this. So you can turn it from one into the other. The problem on a big telescope with having your viewing point out here is as the telescope starts going around and pointing to different spots, you start turning upside down, and then you get sick, and you can't get the data in. Okay, so are there any questions about that? Next, let's go to the microscope. Okay, now, in order to understand the microscope properly, we should probably start with a simple magnifier. That's just a magnifying glass. We've seen this before. And we need to see how a simple magnifier works so that we can get the proper expression for the magnification for a microscope. The idea with a simple magnifier is that what you really want to do is kind of like what you were doing with the telescope. You want to put the image just inside of the focal point of the eyepiece lens. Okay, and so if you were just looking at an object without the magnifying glass, it would have this kind of an angular height, theta. And so we could think of theta then as being y over your viewing distance. Okay? And so this is where you'd put the slide, if this were a microscope or something. Or if you're reading a newspaper, that's about 10 inches away. So maybe something like that, and then you try to bring it in. But normally, you'd want to look at things at about 25 centimeters away. And so that's where we're going to put this thing that we want to magnify. And so that's the original angular magnification, theta. And so again, we're using angular magnification to explain this. Then we could also look, well, what happens if we have it close to the focal point? Then as the light goes in, it's going to refract as parallel beams. Because any source of light that comes from the focal point is going to come in parallel. And so you're putting this object just inside the focal point, but not quite there, just inside. So here, near. We want the object near the focal point, so that the light that comes through is going to be greatly magnified in angular size. And so that's going to be our theta prime. Okay, so how do we get theta prime? We can think of theta prime as being our height divided by the focal length of the lens, f. Okay, and so if you think of this as also being your height here, then in the first case we're looking at this triangle, and we can say the tangent of theta is equal to y over 25. Right? And so that's approximately equal to theta. So that's our theta naught that we're talking about right here. And so that's from this triangle. So this is the angular size, that's without the lens. So that's what that's the angle you're looking through to see this thing at 25 centimeters away. And that's a little less than the focal length. The focal length is a little bigger than that, but not a lot bigger than that. Okay, and so then when we want to do theta prime, we can look at this triangle here. And this triangle is, here's your eye looking at it. And so it's expanding the light out through a bigger angle. So you can say theta prime is equal to that same y value, because I'm just taking this, and this is a line that's parallel to the axis. So this is still y, even though it's not the source of the light. It still has that height y divided by f. And so that I'll call theta prime. So what we get then for, and this is called a simple magnifier. We say that the magnification then is theta prime over theta naught. And so that's just 25 over f. The y's cancel, just like they did in the last example. And so we get the magnification of our simple magnifier is 25 over f. And of course, this is assuming that we're looking at an object typically that we would want to have 25 centimeters away.
What's the difference between 25 and f?
25 is a little less than f. Because it can't be right on f, or then these rays truly will be parallel. But it's close to being parallel. And so it's just inside of the focal point. So that was the point in the telescope too. You wanted the image from the objective lens to be just inside the focal point, because we know that if the object distance is less than f, we get a virtual image. But if O is equal to f, we get infinite magnification. So we want it to be less than, but approximately equal to f. So we want it to be close to f, but not quite there. Any other questions? Yeah.
So the object distance is 25 and the frequency is a little bit...
Not frequency. Focal length.
I'm sorry, the focal length is a little bit less than 25?
Here's f. See how it's bigger? This has to be inside to be a virtual image. So the 25 has to be inside of the focal length.
Gotcha.
To be a virtual image.
And
So that's what I'm showing over here. Yeah, this says O is less than f.
Oh, I see. Okay.
O is less than virtual.
Gotcha.
Any other questions? All right, so with that in mind then, and this is just an approximation. It's not exact, but it's close enough, because I mean, a lot of times you're using spherical lenses anyway, so that your ideal curvature is a parabolic curvature. You've got little ripples in the thing, and so this gives you roughly what your magnification would be if you had a viewing distance that's about 10 inches away. 25 centimeters is about 10 inches away, like you're reading a newspaper, but then you're trying to bring in the newsprint, or like reading glasses. That's what reading glasses mean. is that it would take, you're reading something, and you'd have something that had the right focal length to bring it in at 25 centimeters. You hold your newspaper there, and then you can read it. Now we go to the microscope. And the microscope, basically what you want to do here is, here, instead of having an image that's really far away, like on the moon, you want to have your image on a slide. And that slide is going to be close to the microscope. So here's your microscope. Okay, so here's your source of light there. So it's just a little distance away from your objective lens. And then this is your eyepiece lens way up there. That, because it's so close to the objective lens has to be more curved. And this eyepiece lens is less curved. So it's the opposite of a telescope. Because with a telescope, the objective lens is less curved, and then that's why the telescope's so long, is it brings the image to a point of focus, and then just right in there near the eyepiece lens is where the image is formed. And then you can pop out eyepiece lenses anytime you want to get more magnification in a telescope. But in a microscope, it's the objective lens that you shift. So you can rotate the objective lens around, but you keep the eyepiece lens fixed. And so a lot of the things about a telescope, in a way, are kind of the opposite for a microscope. And so here we've got our more curved lens. Here. And this is your less curved lens here. And so then you want to, but again, the basic idea is the same as with the telescope, in that you want this image to form just inside of the eyepiece lens. It's not really showing it as being quite as close as I would like in this picture, but I'll show you a picture that I do that actually puts it a little closer, which is kind of where I like it to be. And so you want that image then to be the source of light for the second lens. So you put it just inside of the eyepiece lens, and then it's like a simple magnifier. And because you're putting, the image is just like a source of light. So if you put it just inside of the eyepiece lens, then from that point on, it's just like the simple magnifier that we looked at in the previous problem. And so what you want then is a magnification, and oops, I'll pass out these notes to you next time too, so that you'll have copies of this. But for the microscope then, see what I've done here is I put it just inside of the, here's the focal length for the objective lens, FO. And then you want this 25 centimeters. Let's just say it's 25 centimeters. It may be a little closer depending on the design of the microscope. You might have it less than 10 inches away. Then this might be 5 centimeters. Okay, but let's just say it's 25 so we can keep that part of it consistent. Then from here on, it's just the magnification for a simple magnifier. So the total magnification is the product of the two individual magnifications. For the first one, this is just going to be I1 here divided by F0, which is the focal length of the objective lens, times 25 over FE. Okay, so that's the product of the two magnifications. For this one, it's just the image distance divided by the object distance. The object distance here is 25 centimeters. And then from there, we want, well, this actually could be closer than that if you wanted to. But this is going to be, you want this to appear at 25 centimeters away, so that this part of the diagram is the 25 over FE. So you've got I1 over FO divided by 25 over FE. So that's your magnification for the microscope. Are there any questions about that? And so then anytime you want to, you could go back and go, well, I want a little different magnification. And so then you just flip lenses. So you flip to this one, or you flip to that one. Okay? And so that will change the focal length of the objective lens. And so where the image is going to form is always going to be pretty much the same distance. It'll be up here, because you're not changing the eyepiece lens. That I1 distance is something that would be given to you for a microscope, because it'd always be the same. And then you would change the objective lens, and so you'd have I1. This is given from microscope design. Because here, you got your lens down here, it goes up like this, and the light comes together at some point that's just inside of the focal point for the eyepiece lens. So here's FE there, here's the image, and so this distance here, this I1, is defined. But it would have to be given to you from the particular design of the microscope you're looking at, because the eyepiece lens never changes, so you'd always want the image to be at the same place. But then you can still do a little bit of focusing to adjust for variations in your eye. But then you can flip around here and then this is your magnification. So when this is given to you for the particular design of your microscope, then you can adjust this for different magnifications. So you might be looking at a little hair follicle, or then you might want to increase your magnification and be looking at a cell, maybe a bacteria or a eukaryote cell or something like that. And so then you'd want this focal length of the objective lens to be smaller, to be more curved. So you flip to one of these. But then you keep the eyepiece lens the same. And so the thing with a microscope, remember with the telescope, you wanted the telescope to be a big, huge light funnel that brought in light, because if you're going to magnify, you have to have enough light to magnify. And if there's just a little bit of light coming from a distant star, you don't have enough light to magnify unless you scoop up more light with a bigger objective opening. Why isn't that true of the microscope? Why don't we need a really huge objective lens here to scoop up more light from a dim object? What do we have available to us that can give the microscope more light?
A light.
Right, we can backlight it. Or with some of the microscopes I've seen that they sell to kids and stuff, you can just take light from the sun and reflect it up through. And that gives you the light that you need. But you can produce the light that you need by backlighting your slide. And then you make your slide kind of thin so that the light doesn't have to dissipate as it goes through a lot of material, and it can just illuminate your source better. Any questions about the microscope? All right, next, I want to take a look at the third way in which light rays can be diffused.